Yes, so there is a construction of such a space, okay? If you haven't seen it, what's important is to understand that this thing. So if you're also not maybe, what do I mean by structure group? You actually know examples, and examples were mentioned in other lectures. For example, if X is just R4, you can start with homeomorphisms of R4, but then maybe you want to improve that to diffeomorphisms, right? So that would be improving. So this means you have a R4 bundle over your space where you're just using, the transition maps are just homeomorphisms. But if you can manage to improve that to diffeomorphisms, that means you have a smooth bundle. But then in diffeomorphisms, you have those which are orthogonal, so that and that reduction of the structure group from diffeomorphisms to O4 is exactly choice of a metric. So it's a consistent choice of making these transformations linear. But then, of course, you can actually go into SO4, which is a choice of our orientation. And then another thing that was mentioned is actually spin 4, which is actually all these were inclusions, but this one is this double cover. And if you can go even further, if you can reduce your structure group there, you have a spin structure, okay? So I just wanted to show you how this is something actually familiar, except that you usually maybe don't think of BDiff. You think of BO, right? And for O4, the classifying space, BO, is modeled by Grassmannians, right, of 4 planes. And you actually see this, so you can think of a point in BDiff of X as a manifold that sits inside of R infinity and is diffeomorphic to X. But the choice is not specified, okay? Not specified how, right? And then you can compare this to BO, to Grassmannians, which is just 4-dimensional planes in R infinity, right? But you don't specify like a linear, map to R4. The same way you can think about BDiff of X, okay? So this kind of, this means that if you think about maps from Sn to BDiff, and this is what Watanabe constructed when X is S4, but okay, if you have a map from Sn to this, well, they up to homotopy, right, are exactly this set that I wrote like this. This is just maps up to homotopy, right, where Y is a Sn. So this really corresponds to bundles, with fiber X. Over Sn, right, up to isomorphisms of bundles. And then the structure group is diffeomorphism. So I mean smooth bundles, so bundles where your transition maps are diffeomorphisms. Okay, and then, so what are maps of Sn up to homotopy? Well, this is just the end homotopy group. Okay, and then our exercise is that this is actually shifted homotopy groups of diffeomorphisms of X. So you can just start thinking about bundles over Sn, and then the key, hint for this exercise is something called the clutching construction. And you'll actually see the example when n is 1 today in my lecture. Okay, so I just wanted to say this. So we're on the same page when talking about BDiff. So let's recall. Any questions about this? Okay, so recall that given a trivalent graph gamma, we define its degree as the half of the number of vertices. And then Watanabe construction for a particular embedding of gamma into X. And X can be any four-manifold. The construction works. You embed it, and then you define this link. You do surgery on the link, and it turns out that that there is like here degree of gamma parameters. So link is not one link, but it's a family of links, right? Because some components are allowed to change with parameters, and there's that many parameters. And then for each of that, you do surgery, and you get a manifold diffeomorphic to X, right? So what do I mean by this? So let me be more concrete. Let's say that I think of the sphere as degree gamma parameters from 0 to 1 modulo boundary. So inside of this, I think of T1 to Tn n parameters. For this, we assigned this link L gamma T. So it depends on these parameters, the embedding. And then we can do surgery on it. So we do surgery on X along this link. And now observe that, we had some, this link had some, so for example, for the theta graph, if you remember, here I had Borromean link, which was really a link, a single link with two spheres and one circle. But here on this side, I just had one sphere and two circles. But these circles, at any fixed parameter, they were really just forming an unlink. There was nothing happening. What was happening when time changes was that this circle went around the sphere. So this component was maybe like this, and there was like a sphere here, and then this was linked with that sphere. Sorry if this is small. So there was another sphere here, and this circle moved around that sphere. And only when it moves, it was a link. But when you just take one circle on that sphere, this is actually an unlink. Okay? That's something to convince yourself. So the point is that for any fixed parameters here, this link actually has some components which are not even trivial, which are not even linked, and you can just start undoing, canceling all the surgeries. So it will turn out that this guy is abstractly diffeomorphic to X, but you can't do that for every parameter consistently. Okay? So the point is that this diffeomorphism is not canonical. Okay? I'm just trying to explain why this is a point here. It's something that's diffeomorphic to X, but I don't want to say how.
So could you just remind me where are the parameters in the picture?
So parameters came from the fact that in every graph, you'll have to pick some orientation of edges. And then you will decide if you have, depending on these, on every different vertex, you will look at how many spheres you have and how many circles. Basically, those outgoing mean that there will be two outgoing means two spheres and one circle. So here I put like this type 1. And then you have to consistently orient your edges, and it will turn out that you will, so there's some kind of a combinatorics, that there's exactly half of the vertices are type 1 and half are type 2. So that means half of them will just be Borromean rings that's standing still, and half of them will be moving, have one component that moves. Half of the vertices, but that's exactly the degree, okay? So for example, here there's like 4 vertices, 2 of them will be the moving type, and 2 of them will be still. And two of those parameters will be these parameters. Okay? Okay. Okay, so again, just to repeat, the theorem that also in the rest of the course I will try to sketch the proof is this theorem of Vatanab that that when you take X is S4, right, you have that diagram that here you have B diff of S4. Here you have trivalent graphs. You take maybe linear combinations. So you take just a product of diffeomorphisms here. So here, graphs that are trivalent of degree n. And then, so you just linearly extend. Like say you send graph gamma to any choice of embedding G, and then do this construction on that. Also, okay, so not only you need to pick an embedding, but also orient the edges. So it's also a choice. But never mind, we can make some choices. We do that, and then it turns out that this invariant, this Kontsevich integral, will land here in, again, graphs, but modulo relations of antisymmetry and IHX. They were maybe on the slides last time, and they are discussed in this discussion session. So I will not repeat that here, but anyway, we can take the class of the graph gamma in that quotient. But here we have to take, so I could have written here Q, but I prefer to actually call this guy just to tell you that there exists some notion of this group of graphs, even integrally. It's important for my lecture. But then we kill all the torsion elements. And then the theorem is that this exactly goes, to gamma. And that, as a consequence, has that this map is surjective. And because we can compute ranks of these groups in some low degrees, and they are explicitly computed by a computer, and then you can say, oh, there is many classes actually here, and that was not known before. So this proves Smale's conjecture, which was not made really by Smale in this dimension. But basically, diff of S1, diff of S2, and diff of S3 are all contractible. So I don't know. I think Smale would not conjecture it for S4 because S4 is different. But anyways, now we see that the diff following from this theorem follows that diff S4 is not contractible. Oh yeah, so like I should do the boundaries. Yeah, let me not go into the details of the differences. Yeah, thanks for that. Pi n, sorry. Yeah, and here everywhere I could write D4 because we're never using this infinite point, right? Everything's supported in a ball when we do these constructions. So maybe I write it like that, so that just to, in S4 you have also the rotations of the action of the orthogonal group, but yeah, I don't care about that. Sorry, what was the question? Okay. Z, sorry. I probably was saying Kontsevich and then, yeah. Okay. Okay, let me get to, so my main goal, so again, the invariant will be discussed in next lectures. My main goal is now to maybe relate this to some other things. Yeah. Yeah, I am sweeping that under the rug, yes. Yeah, so what I said is that for these parameters, I do this surgery, right? I need to make sure that when one of the parameters is 0 or 1, that I'm canonically X. This is kind of my base point here. And it's possible to do basically because the base point, for 0 and 1, this circle is really at its base point. It's always going to be, like at one vertex, you're going to get circle which is not yet started going around the sphere. And so that's kind of a canonical way to trivialize that. As soon as it starts going, that circle starts going around that sphere, you don't have a canonical choice. That's roughly the explanation. I mean, this is what happens at one of the faces of this. One of the parameter is 0 or 1, which means circle is back at its base point. So it hasn't started going around that sphere. Okay? In Vatanab is, the way he wrote it up is a bit more complicated. I should say that. And maybe also Jianfeng will give you another description that's closer to Vatanab's original description of the same constructions. Yeah, it's a bit confusing, but there's many ways to describe it. And what I wanted to do is describe it in some way that I like. And in particular, tell you this theorem. So in fact, this 2 times E component link right? For every edge, we had two, every edge is replaced basically by a Hopf link. So for every edge, you have two components. This a huge link, LGT, or family of links, family of two E-component links, LGT, can be reduced to just a two-component link. Given by S1 and S2 in X, with even S2 not moving, but S2 fixed for all parameters. Okay, and this is the theorem of Botvinnik and Watanabe. Maybe 2023. They say that there exists. Okay, so what does that mean? If even S2 is fixed in X, remember we want to do surgery at all times. So why not, if this is already constant, we can just do the surgery throughout. And when you do, and this S2, sorry, and S2 a fixed unknotted sphere. So it's a small, X might be huge, but this S2 is a small local sphere in S4. So what happens when we do surgery on that S2 in X? Okay, so this is again for something for exercise session. What happens is that when you do surgery, you remove it. So what remains is this little meridian of that sphere. And actually, there is this three ball that is bound, intersects in one point. For every other point on that meridian, you have a D3. So you actually get, when you do surgery, that S2 in X, you get X connects some S1 cross S3. Let me do it just for the X is S4. So this is the setting that I think they did. There is a family, let me call it attaching spheres, G, T, of S1s in S1 cross S3. Okay, it should be framed such that, if T is in the boundary of this cube, then AGT is just the base point, so it's just S1 cross a point. Actually, Watanabe's class can be obtained as follows, as the following composite. You take S to degree gamma. So for every parameter T here, what we do is we construct a manifold that looks like S4 cross I. Okay, I'll have to explain this notation. And then, okay, or maybe like this. And then we restrict just to the top. Okay, so I'm saying that the Watanabe's map there actually factors through as follows. You can actually build a Cobordism that's really actually diffeomorphic to S4 cross I. Namely, you send the parameter T. Okay, let me do it on the other side. You start with, you're going to build a Cobordism. You're going to start with S4 thickened, let's say 0 epsilon. There you're going to add, right, and so you do that for every parameter T, okay? This is a construction for every T. You will attach a trivial one handle. So 5-dimensional. So that means at the top here, you see S1 cross S3. Here at the bottom, you see S4. And then you will attach two handles along this family of circles, okay? For every T, I have a circle, so I attach a two-handle there. So this is a two-handle, again, 5-dimensional two-handle attached along AGT. And so what I have at the top, well, it turns out that all these are isotopic to S1 cross a point. And you know that if you attach a two-handle to S1 cross a point, you will kill this S1, right? You attach a two-handle that kills that S1, and you're getting back S4. But what I do is I am attaching now two handles along things that are only isotopic to that canonical guy. So I don't have a canonical choice to identify with S4. So here I get a manifold X such that X is diffeomorphic to S4 because this two-handle is canceling this, right? But I just don't want to say how for now, okay? You see? Because I have these many parameters. For every fixed parameter, I know how to cancel, but how do I do it in the family? So this is something they showed, and I want to demonstrate today this for n is equal to 1 and show you how actually Watanabe's classes can, in my mind, they have a simpler description and actually also very useful. Okay. So what do we have when n is equal to 1? Well, again, we have just the, maybe I'll do it vertically here. We have just this graph, which I've been drawing many times. Then we have the Watanabe's construction. This is a class, maybe like this, Watanabe of some embedding of theta. Well, do I want to do it in S4? Let me try to do it in any X, okay? Any 4 manifold. Because as I said, although his proof, his invariant is for S4, there is no reason, not to try this construction in other 4 manifolds. You can still do his construction. We just don't know if they're trivial or not, right, a priori. So this is a class now in pi 1 of B diff of S4, or let's say, I said X, okay? Relative to the boundary. So this class, we embed it somehow in X, but not near the boundary, not hitting the boundary. And so, for example, where does his class live? Well, it lives in A1 tensor Q. What is A1? Well, it is really just like a linear span of just a theta graph. That's the only one in this degree. And then you mod out by antisymmetry and IHX. IHX doesn't actually have a meaning here, but then antisymmetry will actually tell you that theta is equal to 2 minus theta. This is something that was mentioned yesterday in the discussions. And so this is actually ZMO 2. I mean, A1. Okay? So I want to point out this important detail, and that is that Watanabe's construction works integrally. You can still construct these classes. You still construct this ZMO 2 class. For example, in sorry, I should stick to D4 for this, because now I'm talking just about graphs in D4. So even for D4, you can still construct this. It's just that his invariant doesn't live, it lives in a 0 vector space. You kill this two torsion. So we don't know whether to detect it, okay? So the question is, okay, but is Watanabe theta 0 or not, right? And I want to point out that recently was announced by Gabay, Gay, and Hartman, like 10 days ago, actually in the Georgia Topology Conference, I was there. Gabay, Gay, Hartman announced that it's not trivial. It's not the identity. It's not isotopic to the identity. And it's actually, that was known before this. We know that it is two torsion element. Okay, so we know that Watanabe, it's like an involution. Okay. I now want to explain this theorem. How actually theta graph, how does this diffeomorphism look like, okay? Yeah, by announced, I mean that they posted a preprint on archive, which is like a first part of the proof. And they actually do, I would say, something much more general and should be useful for other things. So this will appear in the paper too as an application. Okay, so the question is, what is this diffeomorphism? How does it look like? And here is how I think about it. Now it's going to take some time to draw this. So I want to draw it. Let me orient the edges. Let's say I have two oriented like this and one like this. That means on the left I have two spheres and one circle. Okay, now unlike yesterday when I was drawing spheres with this cartoon picture, like a sphere and a circle that link, now I want to be more precise, and because I think it confused some people. I want to think of these spheres as living in my current S3. And then as I move through time, in the past and future, they bound disks, okay? It's like a usual movie picture, okay? So we are working just in the present. And in the present, I see this circle. Circle will be green. Yeah, this is not green and red like in their paper. They have a particular way of thinking about that, these colors, but I'm not referring to that. Okay, so this is the commutator of these two spheres. Circle lives only in the present, and then sphere moves through time. Now this corresponds to this middle edge. Okay, and now through this upper edge, I need to link this sphere with a circle. So let me just bring the circle closer here. Yeah, I will not worry about the crossings and framings and things like this. So here is a circle, comes there, and here is another circle. I don't know, let's say like this. Okay. Sorry. So this circle links a sphere. Okay. Again, it moves through time. And now what I have on the other side is, again, this guy wants to do a commutator of that sphere and another sphere. Right? But this, we don't want to be a sphere, we want it to be a circle. So that's where with the time parameter happens. So this guy comes here, attaches. So I'll just denote it by this, that this circle moves through time on that sphere with time t. Okay. So now let's show, let's see how Botvinnik and Watanabe reduce this to just one circle moving. Well, this is related to the thing that I mentioned when I talked about claspers in the classical dimension, when I explained how you actually, we do surgery on this complicated link, but you can actually cancel many of the components in that link, but you have to first do slides of your knot, right? That your clasper was attached to a knot. Similarly here, we want to do some handle cancellations. Right, okay, so I didn't explain where the handles come from. So this is related to that. Okay, let me be brief about that and maybe discuss it in the, this thing that, like, if you do surgery on S2, you get, because this is, like, let's say surgery on this sphere, it's a small unknotted sphere, so what you get, surgery on this, gives you X connects some S1 cross S3. And now I actually want to pretend that I attach to one handle. And if you know about Kirby calculus, this is the usual trick that, you don't want to draw complicated one-handle attachments. You actually draw a circle with a dot, and that means you remove something. And this is because somehow, it works the same way. That's somehow similarly, you can think of these red spheres as like we put a dot on them. So instead of thinking of them, they're two-dimensional spheres, so there should be attaching maps of 3 handles. We don't want 3 handles. We want to think of them as giving 1 handles, okay? So red spheres give 1 handles. And green spheres give 2 handles. And we want to do handle cancellation. And you see that, like, each of them, when you think of it, they come in these Hopf pairs, so we should be able to cancel them. Okay, so let me see how I want to do it. Well, I don't want to. I think maybe this will be an exercise for you, but basically what you want to do is maybe you want to cancel, let's say, this pair. right? Or which one? Okay, maybe this one is easier because, yeah, I don't know. Like the point is, for example, here, maybe I want to slide this green over this green so that I can remove later this green and red, right? So like if I do candle slide of this whole band, both of these, over this one, then I can erase this. I mean, that's like the usual way that it works. I'm not going to do it. I just want to show you. And actually, this example is done in my paper that I'm going to mention later. So if you want to see all the moves, I can tell you. But let's say just cancel handles until you get to the following picture. You have just one S2. And you have just one circle. And the way that you think of this S2 is you actually kind of do surgery in it, and then the circle lives in the surgered manifold. Okay? But you actually, it also just lives in the complement. I'm never using the handle that I add to this, like this one handle. So I have this circle, and it will go like this. It will actually go around the meridian of this. And then it will come to itself. And then here, well, maybe I don't want to draw it red so you get confused. But let me say that in the present, it looks like this. In the past and future, this guy moves. So maybe blue. You know, move around kind of the disk that this bounds in past and future. Okay? So this is what Botvinnik and Watanabe have in the theorem. It tells you that, and this is a particular example. So Watanabe of theta is given as, you know, you map S1 to B diff of S4 cross interval fixed on the bottom, right? And this is exactly the Cobordism that's built out of this one handle and this two handle with time. And then when you restrict to the top, you just see the diffeomorphism of S4. Right? So here, what I mean is like you start with, you have S4 cross 0 epsilon. You add this one handle which we think of like corresponding to S. And we add then a two handle along this circle. Okay? This is this Cobordism. And this just means fixed on the top, on the bottom. It's a canonical way to identify with S4, but we don't know how to identify the top, so that's this other map here. Okay, and finally, I want to tell you how to think about this as a diffeomorphism. So this is isomorphic to pi 0. Oh, I forgot to say the exercise. Okay, this was meant to be an exercise when I said pi n of, oh, I actually did. Remember the exercise? Now I remembered. This was the clutching construction, okay? This is exactly what I want to apply now here, okay? So what does that mean? Well, here it's a bit easier because what we have is a bundle over S1, right? So for every time on a circle, right? This is my circle, the base of my fiber bundle. I'm building this fiber out of, you know, these handles. For every time, I have a different two handle, right? That depends on time. That's this one. Is it clear what AT is? Right? It's okay. Maybe I didn't explain. You know, like at A0, it's actually a small meridian. Okay. Then it grows a finger. You know, it looks like this. But then it goes bigger and bigger and bigger until it comes all the way here, and then it goes around the sphere, and then it comes back. So it's back at the base point. It's again going to be a small meridian of this, for which we can canonically cancel, right? So I want to think about this here as times 0 or times 0 or 1, and I want to start canceling. And this is exactly like what I said is a clutching construction. This is exactly how you go from this description to this description. You start canceling, right? What does that mean? Well, basically, on this circle, you know that when you remove this point, right? Maybe just before you hit with t is equal to 1, you have just a d1, and every fiber bundle is trivializable over that. So you just start trivializing until you get close to here, and then you need a way to identify that fiber that you got with your initial fiber, and this is the diffeomorphism. Okay? Yeah. Yeah. Very good question, and unfortunately not. But I'm going to explain that as well. Yeah. Thanks for the question. Yeah. I'm just going to finish explaining. So there, you can see it even more explicitly, okay? And here is the key, how to see this diffeomorphism. So here is a key. Does it look like a key? I don't know. It's ambient isotopy extension. I'm just trying to follow Andrus's advice. Have a joke and a proof. Okay. Ambient isotopy extension. So why is this the key? Well, what is the ambient isotopy extension? Well, we have the family AT of circles in S1 cross S3 such that A0 is A1 is equal to S1 cross a point. And we can ambiently extend that. What does an ambient extension mean? Well, it means a family of diffeomorphisms of the ambient manifold. Each of them is, for every t, is a diffeomorphism such that phi t of this base point sends the base point circle to time t of the circle, and phi 0 is the identity. And this is exactly what this handle cancellation will give you at the top. You want to start canceling, so you know your handle is moving, you're canceling and canceling, so you have to identify, you know, somehow what you get at this complicated time with what you got when this canceling handle was just attached here, right? So what you need to do is ambiently extend this movement of AT to identify all the complements together, right? A0 is isotopic to AT. Actually, complements are diffeomorphic, and they're diffeomorphic through this family of diffeomorphisms. Okay, so it follows that. So do you see what Vatanab of theta is in terms of phi? So what do I get at time 1? At time 1, I have a way to identify, right? Like I'm coming back here. At time 1, I have a way to identify S1 cross S3 with S1 cross S3 such that, so in particular, phi 1 of S1 cross a point is S1 cross a point because A0 is A1 is that. So the family of circles came back where it was, but that doesn't mean that the complement is canonically identified to the complement. Actually, phi tells us how to identify them. So we just restrict phi to the complement of that circle. And actually, everything is framed, so this should be like a little neighborhood of this. So let's say S1 times a little disk around that point. This should, again, be a family of framed circles and so on. So you remove it. So what you're left with is S1 cross D3. Let's say a bigger one. And then you want to get S4 back. Well, you're just going to glue the identity on D2 cross S2. So in total, what have we done? We first took S4. In S4, we took a little trivial sphere. In its complement, we observed this meridian circle. So it really started like this. We started moving this circle we moved, and we followed that by the ambient isotopy. So everything is now moving to accommodate for the circle moving. Everything is kind of trying to escape from it, right? And so that's what ambient isotope extension is doing. Like, circle is moving, all the space is moving, it finishes its movement, comes back, but the complement is messed up, right? And then we remove the circle. In other way, we do surgery on the circle. We remove the circle and attach D2 cross S2, okay? We do surgery on that circle, and that's Watanabe's diffeomorphism, okay? Okay, I should be finishing, so let me just finish by saying my theorem, and then maybe the rest I'll be happy to answer afterwards or in the discussions. So what I proved last year is kind of like a generalization of this Botvinnik-Watanabe theorem, well, at least in the case n is equal to 1. Let me see how I want to say it. So in any x, Watanabe's class for Watanabe G, for any G, embedding just of the theta graph, okay? So I see kind of a way also to do this for other graphs. I just haven't yet, but I wanted to concentrate on diffeomorphisms of four manifolds and not on their families. And then we only use this graph. So any of these classes, Watanabe G in pi 0 of diff of x, is in the image of the following map. You go from pi 1 of framed circles in x connect sum S1 cross S3, which you can think of it as you did a little surgery on a little sphere inside, based at this base point. Then you do this ambient isotopy extension thing, which just like extend ambiently and then restrict to the complement of this. You get a diffeomorphism of the complement of your base point. So it's x connect sum S1 D3 that remains. And then you extend by the identity over the D2 cross S2. So to get to pi 0, to get to this guy, diff of x. So, okay, so what I did in that paper is even more explicit. You can exactly find a class here that gives you concrete Watanabe's class. But maybe referring to your question, this is something that I have studied before independently. So just note, what is this? It's a fundamental group, because this is what this AT is, right? It's a, you start with your base point circle and you come back by some isotopy to that same circle, right? So this is by definition the fundamental group of the embedding space of circles in the manifold, based at this base point. But note that this has dimension 4. This has dimension 1. So this is embedding space of codimension 3, okay? And this is actually what I mentioned in my first talk at the beginning. I mentioned that like there is a third instance, right, where you can do class per calculus, kind of. And that's the thing that I call graspers. So inside of this, you have particular classes which are called graspers, and that are given, okay, let me just draw an example. They are given by, let's say that this is our base point circle here. Then what you want to do, what the grasper is doing, it's going to catch your knot at certain point. You're going to go maybe around some group element G, and then you're going to come back, and let's say, okay, let me say like this. Maybe you do this self-referential guy, like we had before. So you're going to take this part of the circle, go around the group element, and then come back at yourself and do the movement around the meridian sphere. So again, this was this sphere that was moving through time. Here you can do the motion through time, okay? So this is a one-parameter family of circles. And this gives you classes here. In fact, you can completely compute this. You can either use work of Dex. I should mention that. Dax was a student of Serre, and in his thesis, he applies to this case. Or you can use, in a modern language, this is embedding calculus, which again uses configuration spaces and some scanning constructions. And again, a similar theorem like Watanabe's theorem allows you to study this and relate graspers to graphs again. Okay? Okay, let me finish there. I'm sure there is something confusing. Yeah.
So in this theorem, in this statement, so what's the difference? It's just like the proof. What's the difference in the proof when X is a general for manifold? Like
I wouldn't say that really there is a difference in the proof. The whole idea is to cancel the handles. It's just how carefully can you do that so that you know what the end is. Somehow in their proof, it's like they just say it's possible, I think, and they work in a quite big generality for any number of parameters. So the part of the theorem that I didn't say is that, but I tried to explain here, is that here there are explicit classes, and you can say that Watanabe's class is the image actually of a linear combination of classes here that are given explicit in terms of this. And maybe one way to think about this is that actually what Watanabe does is a bit like when you translate, when you cancel handles in the theta graph, you're going to get a very complicated family of circles. It's not going to be the one that I showed. I showed something that looks like this. But in this group, you can show that it's the same as just doing this. So the point is that in this group, you have kind of a explicit classes that you can work with. You have invariants. You know this thing. And so in there, you can show that many things are actually giving the same class. For example, the barbells as well. Barbells also come from here. And then actually, so this is my point of that paper was actually to show that the barbell diffeomorphism, that's something I didn't have time to say, but a particular example is when X is S1 cross S3, and then Badni and Gabay showed that there are many diffeomorphisms of this guy given by barbells. And then independently, Watanabe showed that his theta classes also give classes in there, and you can just check by comparing here that they're the same lists. Mm-hmm.
You mentioned that it's non-trivial to show that this class is non-trivial, right? So can you use this theorem to show that?
Well, I would hope, but okay, yes. You can hope to say, okay, I mean, the first step is to show that something is non-trivial here, yes. And that's doable. But I have these two maps here, so I have to study what dies here and what dies here. So for example, in the case in this case, if you forget about X, if X is S4, this group turns out, just to show you, turns out to be Z infinity times some stupid, not important things. What's important is that this Z generators come from this guy going K times. So you can also say it's like generated by TK, where K is in Z, or maybe like this. Anyways, it has infinitely many generators that look like go K times around the fundamental group, then do this. They're all non-trivial here, but they all collapse only to Z2 here. Basically, even ones die, and odd ones all become this guy, which is 2 torsion. Yeah. So one way to try to prove that theorem that was announced would be to kind of try to study these maps and what exactly they do to this explicit family of things. Yeah. And it was shown, I should say, by David Gay and Daniel Hartman. It was shown that this whole thing does collapse only to Z mod 2. Combined with my work, we knew somehow that this can be at most Z mod 2 generated by Watanabe class. But somehow we couldn't prove that it's non-trivial. That's harder because the whole map could be 0.
Hope that there is some kind of surgery formula relating the configuration space integral of submanifolds and the configuration space of surgery.
Yeah, I would. I think something like that should exist. Yeah. Exactly because for the reason that this is codimension 3, and it's easier to do things here. So embedding calculus works perfectly fine here, and it's much harder to do embedding calculus there. Thank you.